Hi everyone, my name is Josh Long. I'm a Spring developer advocate on the Spring team, a Kotlin Google developer expert, a Java champion, and more than anything, I love production. Today, for many people, the cloud is production. A big part of the movement of software to production, of course, is building software that works well in that environment. And in this video, we're going to take a look at how to build cloud-native services using Spring Boot and Spring Cloud. There are a ton of things to investigate, so let's begin. In this section, before revisiting some of the patterns that allow us to build cloud-native applications, let's revisit some of the features in Spring Boot and see why it has cemented its position as the #1 most useful technology for building applications destined for the cloud. We're going to go to start.spring.io and we're going to build a new application. And I'm just going to call this beautiful Kates, right, for Kubernetes. And we're just going to bring in, I suppose, a reactive web endpoint and the Spring Boot actuator. And that's it. That's all I really care about at this point, I suppose. So I'm going to go ahead and hit generate, and it doesn't really all that much matter what version of Java I chose. The latest and greatest will work just fine. Java 11 is the current long-term supported version. Java 8, of course, is supported for reasons. So there's all that, and you can use any one of them. It doesn't matter. And what we're going to do is we're going to go to our downloads directory, and we're going to build a new application. We're just going to open this application up in our IDE. So here we are, demo.zip. We have a brand new application, and what we're going to do is see that this application is ready to go to production in a cloud platform. Actually, that's actually part of the API, is this idea of a cloud platform. So what I mean by that is that you can actually decorate beans that should be only run in a particular cloud platform. I can say, okay, for example, that this bean should only exist, or should only run conditionally if it's detected that we're running inside of a cloud platform like Kubernetes, right? And so here I can say, okay, well, this is a Spring initializing bean, but it's only going to run, again, when the platform thinks, when the framework thinks that we're running inside of Kubernetes. Now, of course, you can force it to think as much. You can actually change properties here in the application properties file. So you can say Spring main cloud platform equals Kubernetes. Run this code. Right, and there's hello Kate. Now, if I comment this out so that it doesn't think that we're in that platform, and then just restart it, it doesn't print out hello Kate. Now, this is useful. Of course, obviously, when we run an application in production, we want to turn it into a container, right? We're going to want to run it in a Docker image or an OCI image. So what I'm going to do is I'm going to remove that conditional on annotation, because we're just going to look at regular Docker here. And we're going to turn this into we have now a simple application, and we're going to use the class name to just sort of distinguish it. Hello containers from, okay? And the other thing I want to do is I want to change the name. I gave it the name demo, but the thing that we're going to do here will actually create a Docker image for us, and we want to make sure that we don't clash with anything else in my Docker images. So I'm going to use this artifact ID of beautiful Kate. With that done, I want to now turn my application into a Docker image. And the same Docker image I could then deploy to a cloud platform. There's a lot of different technologies that we could use to turn our application into a Docker image. One thing that we've found to be very productive is something called a build pack. Now, this build pack idea borrows from the Cloud Foundry and Heroku ecosystems. It's this idea that we can give it an application artifact, and it turns it into a container that we can then deploy. I'm going to do Maven clean Spring Boot build image, and that's actually going to build the application and turn it into a container by passing the jar through a Java build pack, which will then create a sensible file system that has everything that's required to run this application. And this is actually using a Cloud Native Computing Foundation project called Paketo. There's a lot of concerns that go into running an application in production, things like security, things like memory, etc. But all of that is sensibly addressed here. There's overrides, there's hooks, there's environment variables you can specify, things like that that are part of Paketo. But for the common 80% case, you're going to find that this is more than enough. So now if I go to Docker images, there it is. There's our application. So there's the application that we want to run. This is a Docker image ID. I can say Docker So the application has started up, and there's hello containers from common example demo Beautiful Kate application. So now we have something that we can take into Kubernetes and to other cloud platforms like Cloud Foundry, or anything really that takes a Docker image, Docker Compose, if people use that, Mesos, whatever. We are already off to the races, right? This is, of course, just the beginning. There's a ton more support in Spring Boot for building Kubernetes-ready applications. We've only just begun to cover the support here. We've looked at basic build pack-centric Docker containers or OCI image container generation through the Spring Boot Maven plugin, which is, by the way, also available through Gradle, first of all. And second of all, you can customize in almost infinite variety the generation of the layers in the OCI image from within the plugin. That's the first thing. Second thing is there are other things that we could look at beyond our limited time today. For example, we could look at things like using the actuator to create Kubernetes liveliness and readiness probe endpoints. We could also look at graceful shutdown, a feature that stops any incoming requests and gives the application some time to allow any in-flight transactions to complete before the container shuts down. In this section, we're going to look at distributed locks using Spring integration. You might want to make sure that some resource in your system is accessed only one at a time. In order to support this, we're going to bring in Spring integration, Lombok, and the JDBC support. Let's hit generate. In order to do the work, we need to use Spring Integration's JDBC module. This Spring Integration Distributed Locks support is actually a core SPI with some integrations, or with some implementations. We're going to use the JDBC implementation. We have this now. We can now re-import the project, and now we have to just define the regular code to support the locking infrastructure. So the first things first is we need 3 beans of type default lock repository, another one of type JDBC lock registry, and another one still of type lock registry later initiator. With this in place, we can actually now start controlling access to an otherwise volatile thing. So it's not hard to imagine you've got a service that can only be used one at a time, or you've got some resource that isn't a transactional thing in your architecture that might be accessed only one at a time. In our case, it'll be a file system file, which is a good, simple example. So we have a new file repository, and that file repository is going to guard access to a synchronous file. We want only one thing at a time in the architecture to be able to do this, even across different nodes, hence the use of distributed locks. Now let's create a controller. In order to demonstrate this, we need a web service endpoint. I forgot to add Spring's web support, so let's do that here. Let's build a REST controller, file REST controller, and the REST controller is going to have an endpoint with a name and a time that we should wait before releasing the lock. The first things first, in order to make this work, we need to get access to the lock itself. We don't own the lock, but we want to get access to the thing that we can ask for the lock. In order to do that, we need the lock registry. So we say this.registry.obtain, and we must give it a key, and the key can be whatever you want it to be, obviously. In our case, we're going to use just a static class name. Assuming that class doesn't change over time. There's our lock, and now we want to try and acquire it. So we say if obtain.try lock, and then we want to wait 5 seconds. If we've managed to acquire that, we might throw an exception, so we want to reflect that here in the signature. This is one of those cases where it's useful not to swallow them. Now we're going to use the repository. So let's inject that as well. we'll say this.repository.update, and we want to say hello name at okay. Now, once we've written the change to the file, we want to sleep for the artificial amount that we've been given here to simulate that we're holding the lock exclusively, even though others in the system are trying to use it. Now, all of this will proceed apace, but we want to make sure that when we're done, no matter what happens, that we release the lock. The last thing that we want is for this thing to be exclusively guarded by something in the system that isn't willing to give it back. So we say try finally obtain.unlock. All right, and of course, in retrospect, this might be easier to call a lock. All right, so there's our unlock. And finally, we want to return the read state. So we'll say this dot repository dot read. There we go. Now let's test this out. Now we need to connect this to a database. We're using a database to store the distributed state. Spring.datasource.url equals JDBC PostgreSQL localhost orders. And the password will be username orders, and the username will be orders. Now that we've done that, we need to make sure that we have the right schema in our database table. PSQL U orders orders. D int lock. You can see that table, I've already created that table. You can get the DDL by looking at the Spring Integration JDBC jar. We also need to add a driver, a JDBC driver. Now we can restart the application, and we got to configure a few things. We want to make sure that the application will run on different random ports. So we'll say server.port equals 0. And here it's very important that we make sure you've checked allow parallel run if you're using JetBrains IntelliJ. Let's start the application. Okay. Let's start it again. This first one's on 62793. And the name will be Tammy, and the wait will be 10,000 milliseconds. We also want to talk to the other endpoint, 62824. Localhost Josh 10,000. It's waiting 10 seconds before it releases the lock. So if we go to the file system, cat desktop synchronized file, watch -n1, we can see the things that are happening behind the scenes when we try and affect change on that file. So let's now rerun the Josh write, wait 6 seconds, and then run this. So you can see that Josh, we waited 6 seconds. We've configured our code to wait 5 seconds to try and acquire the lock. So as long as we have less than 5 seconds left in the existing lock, then the second one that started afterwards has a chance of obtaining it. You can see that Tammy eventually got the lock. Now compare that to what happens now. If I restart Tammy's and restart Josh, it would have, since they both started at around the same time, and the writer was only allowing itself 5 seconds to obtain the lock, and it had to wait at least 9 seconds. It wasn't able to obtain the lock, so it never got to. It was still Tammy. In this section, we're going to talk about some of the concerns that only become really important on day 2. Now, when we talk about cloud native architectures, we're talking about software that isn't just working on your machine, it's actually working in production. It's built for production. So we would be remiss if we didn't think about some of the things that we need to care about after we've gotten that software passing basic functional tests, right? We want to make sure that if the application is in production, that it can give us as much information about what is happening. That's all fairly old hat. What I wanted to talk to you about in this section is distributed tracing. This is a very common concern, especially when you involve microservices. You want some way of seeing how messages flow from one node to another. So what I'm going to do is I'm going to create a service called service A, and here I'm going to bring in the Zipkin client. Zipkin will also work with Spring Cloud Sleuth. It's bringing that in transitively, but it's redundant for me to bring that in, but just so you know what's happening. Spring Cloud Sleuth is our distributed tracing abstraction. I'm also going to create a reactive web endpoint. I'm going to call this service A, and then we're going to create another endpoint imaginatively called service B. In order for this to work, we're going to need to use OpenZipkin. So I'm going to go to zipkin.io, and I'm going to download the Zipkin server. Okay, and you can run it as a Docker container or just download it as a jar, right? Which is what I'm going to do here. So we'll do curl zipkin.io quick start, and eventually that'll download. It's like 60 megabytes, and then it'll start up, and you can see it's actually starting up right now. So there's our server. Now we want to connect our services to Zipkin so that they transmit as each message flows through the system out of band this information to Zipkin. So what we're doing is we're sending for each hop in the journey of a message from one HTTP request to another, from one Kafka message to another, or whatever, we're going to send a out of band message asynchronously off to the side to Zipkin. So we're not accumulating a call graph in the body of the request itself. We're just emitting this information, and Zipkin is assembling a call trace, a call graph for us off to the side. So now we've got our services. Let's go ahead and open them up and make them work with Zipkin. So we're going to open up service A, and service A is just going to be a simple HTTP endpoint. We don't care all that much about it. It's just a very simple hello world kind of thing. So we'll say at get mapping hello, and we'll say string hello. And that's it. That's the extent of my Java code. No Zipkin involvement, of course. No Spring Cloud Sleuth. Zipkin was inspired by Dapper, which was the distributed tracing tool at Google. We can use Spring Cloud Sleuth to trace different services. So what I'm going to do is I'm going to annotate my application. I'm going to give it a name as Service A. And I also want to tell Spring Cloud Sleuth how often it should trace something, how often it should sample something. So by default, I think it's 0.1, which is to say 1 out of every 10 requests will be sampled. That's not nearly good enough for me since I'm just doing a demo here and I don't intend to sit here bashing the refresh button just to be able to demonstrate what's happening. So I'm going to do it at 100%. Every single request will be traced. Don't do this in production. Your goal is not to capture every single request in the history of humanity. It's to gather a reasonable sampling of what has happened from which you can derive a picture of the behavior of the services. So I have my service name and I have the sampler probability. Let's go ahead and start this. And we're going to go back to the command line. We're going to open up UAO service b.zip. Now in service b.zip, we're going to act as a client to our other service. So same configuration applies. Spring.application name equals service B, and sampler probability equals 1. Here, I'm going to make an HTTP Web Client call, a reactive call to the other service. So we're going to use the Reactive Web Client. And Spring Cloud Sleuth is automatically going to intercept that web client, and it's going to configure tracing filters on this. So I don't have to do anything else special here. I just make my call as I would normally. So HTTP localhost 8080, and I'm going to expect that the data that comes back is going to be of type string. And I'll just log it out. System out print line. That's the entire call. Obviously, this is a public static void main application. So, I do have on the class path my Reactive Web library, but I'm not using it. I'm using it to keep the process running. But I do need to make sure that we don't block the other port. So I'll start on server port 0. So let's go ahead and run this once it'll start up. It should issue a network call to the other service, which we can then see in our newly launched Zipkin instance. There's hello world. Let's go to Zipkin. Now on the console here, it says that Zipkin is running on 94.11, port 94.11. Go here, go to Zipkin. There's our UI. We can run the query, and we get back this call that I just made from service A to service B, or maybe it's service B to service A. Yeah, service B to service A. So if I click on the details, you can see that it's an HTTP GET method call, that it went to the HTTP path called hello, that it went to this controller class, that it went to this method, and it had this client address, and so on. If I click on the details there, you can see the timeout and all that stuff. And if you really wanted to, you could see all sorts of very interesting information. This is just a single hop. What's interesting is that Zipkin will actually show you distributed hops, right? If I do one service calls another, which sends a message over RabbitMQ or Kafka or anything else, and then it calls another HTTP service, I can see that entire graph reflected in this display here. So distributed tracing is very powerful. It gives you observability. It gives you the ability to see what is happening in your system. In this section, we're going to talk about using Spring Cloud Stream to make short work of integrating systems through messaging. There are lots of different great uses for messaging in an architecture today. The ubiquity of messaging has meant that it needs to be simpler for us to be able to incorporate it into our applications. Nobody wants to fiddle with low-level Kafka, RabbitMQ, JMS, Azure Service Bus, Google Cloud PubSub, etc. APIs. Instead, we can use an abstraction like Spring Cloud Stream to make short work of that. Now, there are, as I say, a lot of different use cases for messaging. Martin Fowler did a great blog a few years ago. So we can use messaging, but we don't want to spend too much time writing code to do that. Okay, so what we're going to do is we're going to create a very simple Spring Cloud Stream application by going to start.spring.io. We're going to create a consumer. We're going to use Cloud Stream. We're going to use Kafka. But keep in mind, I could use Kafka streams. I could use Kafka. You can use Spring Cloud Stream with Redux. You can use it with Azure Service Bus. You can use it with, I think, Google Cloud PubSub. You can use it with, all sorts of different things. But I'm going to be using RabbitMQ, right? So RabbitMQ, and we're going to use Lombok, and we're going to bring in the web support, not because we want to have a web endpoint for this one, but because we want to keep the process running. So we'll hit generate, and that'll be our first bit. The second thing that we want is a producer, so we're going to generate that as well. So we'll go to our code, producer application. And I'm going to write the Java code first. We're just going to create a simple HTTP endpoint that returns a Boolean when we send a message. Send name Boolean send. And in order to send that message, I'm going to need a pointer. Let's see. We're going to make this a controller. Greeting REST controller. Okay. Put that down here. Good. And in order to do that, we're going to need the pointer to the source. This is the Spring Cloud Stream messaging source interface. And I'm going to tell Spring Cloud Stream to inject that into the constructor. I'm going to tell Spring to inject the source into the constructor. And I'll tell Spring Cloud Stream to create a binding based on this interface. Now, a source is just a regular Java interface. You could create it yourself, and you could use your own. It's at output message channel. You can create as many of these message channel definitions with the corresponding output or input annotations as you like. Once you've got that done, you can tell Spring to enable the binding, and then we have to configure it in the property file. We'll configure the link between that abstract channel definition and the exchange in the RabbitMQ broker in just a second. So we'll say source.output, that's the message channel. And what I want to do is I want to create a message. I'll say message equals message builder dot with payload hello world, okay, dot build. There you go. There's my entire message, and I want to send that out. I'll say output.send build. And here, I'm going to just return that output send call there as the Boolean. And That's the entirety of it. That's the entire of my Java code. Now I'm going to configure the binding. So I'll say Spring Cloud Stream bindings.output. And again, this part is it corresponds to the Java interface there, but and because of that, it can be whatever you want. And then it's going to be called CNJ messages. Okay. Now that exchange isn't linked to a queue, and that queue isn't bound to an exchange. None of that has been done already. So I'm relying on Spring Cloud Stream to create that machinery for me. It's just one of those things where whenever Spring Cloud Stream can help me, it does help me. Okay, the application's up and running. Let's now go to the consumer and do the opposite. We're going to consume. So we'll go to the consumer application, and here we'll say @enable binding sync.class. Okay, sync.class, and we're going to make this a stream listener. So stream listener, I'm going to tell it to listen for messages, new message, and we could actually get the whole message object if we wanted to. We could pick that apart and get the headers and all that kind of stuff. We could also use @payload and @headers to inject individual payloads coerced to a particular type if we wanted to. But for our purposes, I'm happy with this. So we can say system out messages or message.get payload, and that's it. Right? That's the entirety of the application. But again, we need to do some configuration. Spring Cloud Stream bindings dot input destination equals, and we must use the same exact thing. So CNJ messages. We have an issue because it's running on the same port. So we'll say server port equals 0. We don't care about the port on this one. It's a web server, but we don't want it to be. We don't care about the web server. Alrighty, so the application's up and running. Now we can go to our service, our producer, and send an HTTP request to port 8080/send/name. So let's get these things left to right. So the consumer is on the right side here. And now we go to the browser, localhost 8080 send world. And there we go. In this section, we're going to talk about centralized configuration, which is another common pattern that you're going to care about when you start moving into a cloud environment. What we want is to have the ability to centralize configuration values, things like the port, credentials, passwords, secrets, even stuff that is environment specific. We want to keep that wherever possible out of the source code and in a place that any application. A natural first cut is to use environment variables. Spring Boot normalizes environment variables and turns them into properties. So if you have a property called server.port, you can say export server_port equals as an environment variable, and that'll be made available to the Spring Boot application that's looking for server.port. But we can go a step further. One of the really interesting opportunities is that we can actually have centralized configuration. One way to do this is to use one way to do this is to use one of the many different configuration servers that we have as part of Spring Boot's ecosystem and the Spring Cloud ecosystem that we have as part of the Spring Boot and Spring Cloud ecosystems. So we could use Zookeeper to store our configuration. We could use Console to store our configuration. We could use HashiCorp Vault to store our configuration. And there's even more. You can actually use Microsoft Azure's Key Vault, right? For example. So there's lots of different options there, right? Google Cloud has one as well, but it's not the starter is not provided here out of the box, I don't think. But either way, lots of different ways to store keys and values in a secure, centralized way. One of my favorite ways to do it is to use the Spring Cloud config server. And the config server version controls your configuration files as Git file. So let's create a simple config client. We're also going to give our client a name. We're going to say spring.application.name equals greetings. Let's just define a Spring Bean, actually. That's a good idea. We'll just say application listener, application ready event. And here, I'm just going to inject a value. And I can use all of the normal mechanisms for injecting values. I can use configuration properties. I can use @value annotations. I can inject the environment object itself. All the stuff that you've used from Spring Framework and Spring Boot, all that still applies. It's just that the value that we're going to be pulling out of the environment sources itself from the config server, right? centrally managed config server. So there's our client. Okay, so it's going to talk to port 8888 for the config server. It's going to give itself a name of greetings. Let's go back to start.spring.io. And here we're going to create the config server. And that's it, I think. That's all we need. So we're going to hit generate. And just as before, we have to configure some things about this. So first of all, server port equals 8888. Second of all, we want the application to have an annotation telling it to be a config server. So we can say @enable config server. And in our properties, we need to also tell it where to find the configuration itself. So Spring Cloud config server get URI. So this is a Git repository that contains configuration files, beautiful.properties and greetings.properties. Spring Boot's going to start up. It's going to look at its Spring application name. It's going to say, hey, my name is Greetings. It's going to ask the config server, what files do you have for the greetings, for the service called Greetings? And it's going to say, hey, I've got this greetings.properties. If I had a greetings.yaml, it would return that as well. So I want to plug in this Git repository, since we know it's the correct one, into this URL here, right? So greetings config repository. This is going to act as a facade, as a proxy for that Git information. I go to 8888. If I open up a new tab and go to localhost 8888 greetings default, I get the information back from github.com, Josh Long greetings config, repository, greetings.prop. This specifies two properties, server.port equals 8000 and greeting equals ni hao. Now, we don't have any web, I didn't bring in the Spring Boot starter for reactive or non-reactive web endpoints. So this server.port property is not going to matter. But we will get the greeting property, and we're going to inject it into this. I have S here, greetings. That's a problem. It's actually greetings. So let's go ahead and remove that. And then we'll restart the application. And the application starts up, and there's our message, ni hao. So centralized configuration is very convenient. We obviously have a lot of other things that we could do. We could refresh the configuration in the config server and use the Spring Cloud event bus to refresh the client so that it would automatically repoll the new configuration upon a change. So we can actually centralize configuration and force all services to reload their own state based on that updated configuration. In this section, we're going to need a couple of sample services. So I've built two different services, one called an order service and one called a customer service. You can see that the first endpoint creates orders given a customer ID. And here, there's no actual orders. I'm not even bothering with the database. I'm just creating a very simple randomized sort of list of records given a customer ID. For the customer service, I'm pre-building a randomized list of customers using random names from a list of pre-configured names. So the endpoint just returns the list of customers as a reactive stream. So I've got these two services. I want them to both be able to participate in service registration and discovery. This is important for what we're going to be doing. So I have elected, when I built them, to include the Spring Cloud Netflix Eureka Discovery Client. Spring Cloud has the ability to talk to a service registry. We can talk to a number of different service registries. I'm using Netflix Eureka, but you could also use Apache Zookeeper, HashiCorp Console, Kubernetes and Cloud Foundry itself, and a number of others. We need to stand up an instance of our service registry in order to do the work. I'm going to go to start.spring.io and I'll create a new Eureka service, right? This is a very nice thing to be able to do, particularly for a demo, but you could use anything, right? You don't have to stand up your service registry with start.spring.io. It just happens to be very convenient. Here's my new Eureka application. I need to do two things. I need to say enable Eureka server, and then in the configuration, I need to specify just the bare minimum. It's up and running, and I can confirm as much by going to the browser, 8761. And there I can see that there are no instances yet registered with this service. So I need to now restart my order service and my customer service. Okay, there they both are. Now I want to talk to both of these. I want to build an API gateway. We're going to use a project called Spring Cloud Gateway, and we want it to also talk to the service registry, Eureka. I'm going to call this gateway service, and I'll hit generate. Spring Cloud Gateway is meant to be a proxy. You define routes that accept incoming requests and then act on those requests before sending them on to their final destination. We can use the route locator builder to define the routes that our system cares about. We're going to use different route specifications. We're going to say that we expect to match incoming requests destined for /proxy, and that we expect those routes to then be forwarded to our downstream service. We could use an absolute host and port. We can use this LB prefix to tell the service to load balance the request by calling the downstream service. Obviously, we have a problem. The incoming request will be proxy, but the downstream service, customer service, doesn't have a path called proxy. So we need to remove the path from the incoming request and set it to be something that exists on the target service, like so. Just for fun, I want to also add a custom header. You see, these filters are where you get a lot of the power out of Spring Cloud Gateway. So we can say, add that. Now, if I deploy this, now we can see that it's working by going to localhost proxy, and it makes a call to the downstream customer service as though it was running on this host and port, when clearly it's not. Spring Cloud Gateway can do all sorts of interesting things. You can also use configuration to dynamically define the routes as property files or YAML files. Those can be version controlled in the Spring Cloud config server. You can dynamically refresh those configuration files. So there's a lot of interesting opportunities. One of the more useful things you might do without any code whatsoever is just to have the locator. And the locator automatically sets up routes for you. I did this the hard way. I used /proxy as the prefix. But now, with this locator, I can go to localhost 8080 /customer-service /customers and make the same exact request without any Java code whatsoever, or at least without any extra Java code whatsoever. The next kind of service that we care about is a Reactive API Adapter. We're going to build a new module called Client, and we'll use the Reactive Web Support. We're going to use Lumbuck, and of course we want to register ourselves with the service registry so that we can read information from the service registry. Let's open this up in our IDE. In order to do our work, we need the order and customer DTO from each project. So let's go copy and paste those. With these two types in our code base, we can now build a client to talk to that downstream service. In order to do that, we're going to need a Reactive Web Client. This is a non-blocking HTTP client that we can use to make HTTP calls to the downstream services. Let's build the client. Now I want to make a call to the downstream service, and here too, I want to take advantage of the load balancing possibilities offered by having the service registry. I can do this by injecting a reactive load balancer filter, and then configuring that on my web client. So now I can just say HTTP customer-service customers. The host will be swapped out. The service ID will be swapped out and replaced with an actual host. I'll retrieve the data, and I'll say that I expect the data to be coerced into a JSON stream, a reactive stream of type customer. Okay, So there we go. There's my entire client. First, let's create a runner to demonstrate their use. Okay, suppose I want to make a call to the client. I say client.give me the customers. And now I've got a reactive stream of customers. Well, what happens if something should fail? There are nice operators that I can use, like for example, retry, or retry 10 times, or retry 10 times and then use a backoff. I can do things like that to make my services more reliable. I can also specify timeouts. I can say timeout duration of seconds. I can also specify that when something goes wrong, I want to degrade gracefully by using an exception handler. So here, I'm given an exception, I'm given a chance to return some other stream besides the one that would have been returned otherwise. So this is one way that reactive APIs allow us to build more reliable services. Another really nice thing about reactive APIs is that if this isn't enough, it's easy to add things without changing the API because, again, every type we're dealing with is just a publisher. There's a nice third-party project called Resilience4J, which gives you the ability to easily add things like bulkheads, rate limiters, retries, and circuit breakers. I'm satisfied, however, for now that we've done enough to make our services more reliable. Let's talk about one of the other big benefits of using reactive APIs, namely the ability to do really seamless scatter-gather kinds of composition. So what I'll do is I'll say customers.flatmap, and then for each customer, I want to zip two streams. I want to create one stream out of the customer and another one out of the orders. So I'll say flux.zip, and the first operand, the left side of the zip, will be mono.just C, and the second will be client.getOrders for customer C.getID. And this gives me almost everything that I want, but what I really want to do is I want to collect all of the orders into a list. So now, if I return this, what I get is a tuple containing the customer and that customer's orders. Now again, these are all references to types that will eventually give me these things. Nothing has been resolved yet, right? If I run this code up until this point, nothing will have happened. I need to subscribe, so this gives us chances to rewire the stream. What I want to do now is aggregate these things into an aggregate type. So I'll create a new one here for my client view called customer orders. Data and required args constructor are in place. Now I can say tuple to flux.map tuple new customer orders tpl.getT1 customer tpl.getT2. There we go. This is my stream of customer orders. Now I can visit each one. Before I can run this, I need to make sure I configure a service ID so I can register with the service registry. Spring.application.name equals client. And I also want to make sure that I disable ribbon. I want to use the Spring Cloud load balancer abstraction instead. There we go. There's our data. We got our custom orders, each of which contains a customer, and each of which contains one or more customer orders, with the customer ID pointing to the same ID as the customer. We could cover so much more, my friends, so much more. But I think we're just going to have to leave it there. We've looked at some of the features that cement Spring Boot's leadership in the containerized cloud platform world among platforms like Cloud Foundry and Kubernetes. We've looked at patterns and principles that will benefit you when writing distributed systems for the cloud. We looked at things like service registration and discovery, reactive scatter gather and service orchestration and composition, client-side load balancing, API gateways, centralized configuration, distributed tracing, messaging, distributed locks, and of course a number of patterns to make service-to-service interactions more reliable, things like retries, timeouts, error handling, and so on. But this is only the beginning, my friends. We've got a ton of stuff that we could have looked at, but again, we're just plumb out of time. If you understand the concept that we've introduced here, then you've already got most of what you need to understand and work with and integrate the various platform-specific integrations. Projects like Spring for Microsoft Azure, or Spring Cloud GCP, or Spring Cloud for Alibaba Cloud, or Spring Cloud for AWS. You've got the fundamentals you need to start your journey to data-driven applications as well. You can use things like Spring Cloud Task, Spring Batch, Spring Integration, and Spring Cloud Data Flow. And we've only begun. There's a ton of stuff that we can look at besides this. You can see that there's a lot to like in the Spring ecosystem if you're trying to build cloud-native applications. It's no wonder organizations like Netflix, Alibaba, eBay, and Financial, and others have all converged on Spring Boot, Spring Cloud, and many others besides to build better software faster. Thank you so much for your time, and I hope this all helped you on your journey to production.